All right. So today we practiced some free body diagrams, but we also talked a little bit more about our vocabulary. So I want you to look back. We talked about Newton's first law, uh, inertia. We talked about the velocity of forces in equilibrium, which kind of is already like number 4 and number 13. We talked about weight and little g, okay, which should sound familiar, okay? So we're covering some more of these vocab terms. Okay? So on Earth, I got a little lazy and didn't color the rest of them. On Earth, um, free body diagrams exist. Okay? We've been talking about our forces. Like let's say we have like a force applied or force sub A this way. In the opposite direction, you would have a force oppositional. Okay? But we haven't really talked about what's on the up and down, what these arrows are called. Well, on Earth, can you think of a force that points towards the center of Earth all the time? We say down, but it's really towards the center. What points down? Well, if you said gravity, that's right. We call it force gravitational, F sub G. Okay, F sub G. All right. Now, you've said force gravitational your entire life. You just said it in a different way. Force gravitational is actually this word, weight. Okay, the word weight means force gravitational. Okay, but usually we think of weight as a mass, right? You think that mass and weight are the same thing, or at least similar, but they're not. Mass and weight are directly correlated. The more mass I have, the more weight I'm going to have on a planet like Earth. Okay, mass and weight are related this way. You can figure out the weight or the force gravitational, these mean the same thing, by multiplying the mass of an object times g, little g. And if you remember little g from free fall, little g had a value of 9.8 meters per second squared. And right now you might be thinking, hold on a minute, meters per second squared, isn't that acceleration? It is, right? G is the acceleration, little g is the acceleration on Earth when you drop something. It's the amount that you're going to accelerate towards Earth. This is for near Earth's surface. For my class, I like to use 9.8, but really you can use this value as well, 10 meters per second squared, and this is acceptable to use for g as well. It just makes things easier. Okay, so you can actually figure out the weight or the force gravitational of anything by multiplying the mass times the gravity. Okay, so mass, let's say Mr. Bayona's mass is 64 kilograms, right? Okay, so if I have the mass and I know I'm on Earth, I always have little g, and I have the mass right now. So I can figure out the weight by plugging in mass 64 and little g. I'm going to go ahead and use the easy one for right now. 10 meters per second squared. You get 640. Now, what's the unit for weight? Is it pounds? No, it's not pounds. Not in scientific community, okay? Not in the system international. Well, look, what were we trying to figure out? The force gravitational. Well, what is force measured in? Newtons, right? So weight is actually measured in newtons. Force gravitational is measured in newtons. So just remember that. Now look here. We said that A is actually equal to G. So look what I'm going to do here. This equation isn't new. This is actually just G. And instead of force net, we're doing force gravitational. Okay, so all we did is we rearranged this equation to figure out what the force gravitational or weight, the weight is. Okay? Okay, cool. So we just multiply by m, right? Now we have mg equals F, right? Make sense? Okay, now. We said that Newton's first law, or we're learning about Newton's first law, says that an object in motion is going to stay in motion. Object in motion is going to stay in motion. The only way for it to stop that motion is for an object to force it to speed up, right? So if something's at rest, it's going to stay at rest. Isaac Newton said in his first law that objects are lazy, right? But he used a different word for that. Okay, well, we'll get back to that in a minute. Imagine there's a semi-truck. Imagine there's a semi-truck rolling down a hill. Okay, imagine there's a semi-truck rolling down a hill like this. You can imagine it's really, really, really hard to stop because it's really heavy, right? It has a lot of mass. Semi-truck on a flat surface would also be very, very difficult to move because it's very lazy. Okay? That laziness he called inertia. So the first law of motion is actually inertia. Okay, the first law of motion is inertia. Okay. Now, if I made this semi-truck or train or whatever, if I decided to compare it to something that was bigger, right, is it going to be more lazy or less lazy? Is it going to have more inertia or less inertia? Well, this one's going to have a little bit of inertia. This one will have a lot more inertia. In other words, it's harder to get it going, but it's also very hard to stop because it's bigger. Now, what quality about these two trucks do you think is going to make it more lazy or give it more inertia? I'll give you a hint. We worked with it in the last one, right? The mass. The more mass something has, the more inertia it has. The more lazy it's going to be. The harder it's going to be to stop. So you can think of this semi-truck trying to go in a circle, right? Trying to go through like a circular bend, like on that I-10 or something, on I-10 or something, right? If it's really wet and slippery, guess what's going to happen? This guy's going to try to go in a circular path. So if I can draw a circle real quick. This guy's going to try to go in a circular path. But what's going to happen? Instead of going in a nice circle, I'm going to slip and then skid away. Turning is acceleration, which takes force, right? If I don't have any force, I'm going to stay in a straight line, which is part of inertia, part of the first law of motion. An object going in a straight line motion is going to stay that way unless something like force friction forces me to turn. So the velocity of an object, like in space, right? If I were to take this truck and push it out into space, it would go forever until something forces it to turn or to speed up or to slow down. Okay? That is the law of inertia. That's Isaac Newton's first law.